All right, good. Let's move on. So our next talk is by Fabian Ruehle, who's going to tell us how to explore the space of 60 little string theories. Please go ahead.
All right. Yeah, thank you very much for this great workshop and for giving me the opportunity to present my work here. Yeah, the title, I wasn't quite sure what title to give, so I gave Exploring the Space of 60 little string theories. This is what this is mostly about. But most of it actually has to do with sort of twisting some center symmetries and matching degrees of freedom across different T-dual theories. And the work is based on work that has been done, I'll actually switch to this one, has been done in my group with my student Hamza Ahmed and my postdoc Paul Ullmann. A second part I want to talk about has been done again with Paul and Florent, and a third part with Paul and Benjamin Sung, who's a postdoc in Santa Barbara of Dave Morrison. So all of these have a Boston connection. Ben was a student in Northeastern. Florent visited Northeastern and we started this project, which now came out. So I figured at that point we might just as well, instead of calling it twist in the center, we might just as well call it T in the Z and a match of freedom. So let's run with this. Good, so we talk about the string theories. Essentially, the way we construct them geometrically has been well understood thanks to Kurmun in '96. So we have a F theory, we have a T2 vibration over some base. And if you want to give this more structure, essentially you have two choices. In the end, we want to decompactify a curve in here. And then Oguizo tells you essentially this can have two structures. Essentially, you could have a K3 vibration over P1, or you could have an abelian surface over P1. So we have these two choices, and then we decompactify this P1 here to C, and we get then something that's called a heterotic LST if we choose this route, and we get something that's called type 2 LST if we choose that route. Good. So these LSTs are interesting for various reasons. One of them is if you have a 6-2 supergravity, you can decouple gravity and you either get to an LST or get to a superconformal field theory. So gravity is decoupled in both. The difference here is that an LST has a non-contractible curve, and this curve has a volume on a scale associated to it called a little string scale, which is of course absent in SCFTs. So in some sense, these LSTs are more like supras. They are UV complete in 6 dimensions. They do have an intrinsic scale just like supergravity does, and they have T-duality upon circle compactification. So in some sense, they provide an interesting playground to study the landscape or the swampland. So you might ask, how much of the swampland is actually due to having a scale in the game? Typically, the scale is the Planck mass. In this case, we have a different scale. You could ask sort of mathematically, how much of all these finiteness constraints that we see in the swampland is actually due to just having a compact Calabi-Yau, because in this case, we now have a non-compact Calabi-Yau. And you might ask sort of how much of the swampland is due to being UV completable. Typically, you UV complete into gravity, but in this case, you UV complete into something else. So understanding the landscape here and the conditions that you have from sort of a bottom-up field theory perspective on LSTs versus a geometric construction motivated us to look into this. Yeah, so this is the collaboration. I will talk about first sort of results we did in the context of heterotic LSTs. Then I will talk about frozen singularities. This was done with Ben, and type 2 LSTs. Okay, so in the first project, as I said, we do heterotics. We start with the K3. And then what this T-duality means, you have the 60 LST. You do a circle compactification, let's say. You allow yourself to turn on some flavor holonomies at infinity. So this is something like that would have been a Wilson line in a compact case. This takes you to a 5D SQ symmetric quantum field theory. Then you move in the Coulomb branch and you get to some theory here. If you have another elliptic vibration in here, you can do another circle compactification. You can also move in the Coulomb branch. And if you can get to the same theory here, then we call these two theories with the two different elliptic vibrations in here a T-dual LST. So that's the definition. And we are now interested in essentially finding invariants such that this commutes. So we are interested in looking at the 6D model and finding necessary conditions, things that cannot change under sort of circle compactification plus Coulomb branch motion plus Coulomb branch motion plus lifting. That's the setup of the program. And from the top-down perspective, essentially, we use the same Calabi-Yau, just sort of we have different elliptic vibrations in there that we use sort of upon circle compactification to build this up. So essentially, things to look for, invariants to look for, should come from some topological properties of this of the defining case here of the Calabi-Yau. From the bottom up, what we do have is essentially just have the anomalies as usual. So we have this anomaly polynomial here. And then this is in general, of course, these anomalies are non-zero, so you need to cancel them by modifying the Bianchi identities for H3 here. And yeah, so there are sort of well understood modifications. The tensors in here, there's sort of a tensor that is singled out, and that is the tensor that has to do with the little string, meaning sort of there's a non-contractible curve in here. If you look at the intersection properties of the base, there's a zero curve in there because we need one that is non-contractible by definition, and sort of the linear combination that corresponds to that non-contractible curve is then what's called the LST direction, and then we have the other ones. And the coefficients that appear here in this modified Bianchi identity, they are called two-group structure constants, kappa r and kappa p. And then there's also this kappa f, which appears for the flavor symmetries. Good, and it has been argued in a series of papers that essentially the dimension of the 5D Coulomb branch has to be invariant, and this is given in terms of the rank of the gauge group and the number of tensor multiplets, so this is already encoded geometrically in the Calabi-Yau. And also these two-group structure constants have to be invariant, and they have been calculated to be for the heterodyne, the type 2, just either 2 or 0. Kappa f, the third one here, this one cannot be by itself an invariant because the flavor group is changing. But we argue that sort of from a geometric point of view, while the different flavor groups can change, the rank has to stay the same. So you would expect that kappa f itself is not an invariant, but the rank of the gauge group is an invariant. And we now sort of want to construct this landscape and sort of check these invariants in increasing levels of difficulty and sort of see whether we have found all models, whether we missed some, whether there's something you can find it from the bottom up that you cannot find in the top down, and so on. So yeah, we go through different levels of difficulty. The first one is the simplest one. And this has been understood, again, sort of for a very, very long time. The way to think about this is essentially if you have been around, if you have been a fan of this conference series for a while now, you've probably seen toric top. So this is useful way of thinking about this geometrically. So what you have here is you have some elliptic vibration given by this hypersurface, and then you have 4 points at height 1 and 16 points at height 2. So what this is a trivial top and an SO32 bottom. And if you look at the brown, at the gray one here, this one is also an elliptic. It uses an elliptic vibration, and then you have essentially 6 points here at height 1, 2, 3, 4, 5, 6, and then points at height 2 and 4, and these are the cuts labels of E8. So if I look at essentially the white vibration, I get an SO32. If I look at the gray vibration, I get an E8 times E8. And sort of what has been in the fiber here is now part of the base, and vice versa. So this is a useful way of thinking about this. So we have this usual T-duality between E8 times E8 and SO32, which are T-dual essentially in 9 dimensions by going to the common SO16 times SO16 branch. And you can make this slightly more complicated by modding out an additional ADE algebra. Good. So the next level of complication, you can turn on these non-trivial flavor holonomies, meaning you can break the E8 times E8 or the SO32 to, let's say, E6 times E6. And then we can build something here by fusing together, by gauging. I mean, in this case, we broke E8 times E8 to E6 times SO8, and here to SO8 times SO8, and then we can gauge the common flavor algebra here and sort of create longer theories. And then we can construct the T-dual. In this case, for the E6 times E6, this would be something like SO24 times SO8. And the complication that arises here is that in this case, these flavor symmetries are not geometrically realized. In this case, actually, we need to resort to the quantum field theory or the bottom-up or anomalies to infer what the flavor symmetries are here. If there's more Weyl torsion in the elliptic vibration, then the Dynkin diagram can be folded by an outer automorphism. So in this case, essentially, we have this SO7 and this SO8 sitting here, and then under T-duality, you get a folded Dynkin diagram. And as I said, in this case, you can encounter self-dual LSTs, for example, taking inspiration from just E8 times E8 and SO32 T-duality with SO16 times SO16. You can construct theories that are self-T-dual if you allow for these broken flavor symmetries by holonomies. Good. Next level, non-simply laced gauge algebras. So if you take some subgroup of SO2, you always get an ADE singularity. And the question is that now also if you look at intersection forms, how can these be non-symmetric? So how can you get something that's non-simply laced? And typically the answer is 7-brane monodromies. So in this case, this is not quite so simple because we have decompactified the base. So it's not quite clear how to realize these. But you can construct them from either using freezing fluxes in 6D SCFTs, meaning you have this fractionalization and then you cut this off at a certain point, and then from the superconformal matter essentially that's glued in here, you see you get G2s and F4s appearing. So I can essentially cut this off at G2 here, and then I get this G2 flavor symmetry here, and an gauged F4. Another possibility is you take curves in the ambient space which pull back to inequivalent curves on the K3, and so they come from they are the same curve in the ambient cohomology, but split on the surface, on the Calabi-Yau surface. And since they come from the same ambient space K3, so they are non-Kähler favorable, their volumes essentially lock together, and you can then exchange them by an outer automorphism, and you can fold these diagrams together. And sort of in this construction, for the first time, we also encounter something that is a counterexample to a conjecture that was in the literature. Namely, we can have the same base with two different T-dual theories here. And so what this means is essentially the base geometry here is not, or the base topology of the quiver is not enough to tell you uniquely which theory you go to. And in this case, this worked essentially because we had an E6 here, and this E6 was then folded to alpha and F4. And in E6, you have this triality. Essentially, alpha and E6, you have three legs, and you can fold two of them together in pairs to form an F4, and these two different ways essentially give rise to these two different quivers. Good. Next level of complication is a twisted T-duality. So if you have also multi-sections and not just an elliptic vibration, your flavor theories can get twisted, and this is work in progress, so I will just sort of show you an example. So we start from an untwisted theory. We have an elliptic vibration with a multi-section, then we can get these twisted flavor theories E62 and SU32, and now sort of these can now reduce to two different theories, one that is again untwisted but non-simply laced, and another one that is twisted. So in order to understand whether we have built all the theories, we need to understand sort of all the subtleties. You can have T-duals of twisted theories can be untwisted. We can have T-duals of sort of with non-simply laced things can be related to simply laced, and so we need to understand all these effects, and in the end they come down to properties of the different elliptic fibrations. Okay, the last level of complication is the frozen singularities. So if you take type 2B or F theory, you can exchange a stack of an O7 minus plane with 87 branes to a single O7 plus brane, just on the level of the RR charges. So, and this is in the normalization where the R charge of the 7 brane is 1, and the RR charge of the O7 plus or minus brane is plus minus 4. And in the heterotic string, this frozen phase of exchanging this O7 minus for an O7 plus is known to be related to a model without vector structure in the heterotic SO32 case, or to the CHL string in the heterotic E8 case. So now what we do is we construct the F-theory duals in the heterotic SO32 case without vector structure in the limit where we have a small, or where we have a collection of small spin 32 mod Z2 instantons which collide with an ADE singularity. And then we explain how to read off the divisors in the frozen phase. What you have to do essentially is you have to look at the embedding of the gauge algebras into the SP. So what the freezing does is typically it turns an SO32 into an SP of 8. And then by sort of using the gauge embedding group theoretically allows you to read off from the embedding index how the divisors are changed in the frozen phase. And we also derive a result where we show that essentially the number of 60 neutral hypermultiplets is not changed under freezing. What this freezing does is it essentially identifies or folds curves on top of another, so this changes H11, but H21 is unchanged in this process. And finally, we also explain from the type 1 perspective, and we work out how to read off the matter spectrum in the frozen theory. And essentially, this had been understood for AN, so we did it for the D and the E singularities. And essentially, what this freezing comes down to is you have these actions GI, which are just the orbifold actions of the ADE generators. You have this action sort of representation of the orientifold, and then if you transpose this, this has to be equal to the orientifold action up to a phase. And if you turn on this non-trivial phase, if you set this equal to -1, you freeze, and if you set it equal to +1, you don't freeze. And now by the Mackay correspondence, this essentially just becomes a problem in representation theory of finding the matrices gamma here for the binary polyhedral groups. As I said, for AN it was already done, so we sort of did it for DN and E6, E7, and E8. And if you look at these representations, you see that sort of all of them appear with even order if you look at the presentations, except for E8. E8 has generators that cube and go in the fifth power to 1. And what this means, this is incompatible with setting a -1 here. So essentially, by looking at the properties of E8 here, which is sort of the binary icosahedral group, you can see that you cannot freeze E8, but you can freeze the other ones. And we work out sort of the representation theory. We work out then what these matrices are and how to read off the spectrum. Okay. For the last part, I want to talk about the type 2 LSTs, which is the work that we did with Florent. And essentially much of what I just said can be repeated for the type 2 little string theories as well. In this case, there's no primordial gauge group, which means that the flavor sector is essentially trivial. And indeed, we see that the flavor symmetries are actually also severely constrained from the LST worldsheet perspective by anomaly inflow and unitarity. So if you look at the 4D anomaly polynomial on the worldsheet of the LST, you can write it in, like so. And then you have left moving central charge is then given in terms of these quantities, where this is 2 minus eta II, and eta ij is the intersection matrix. Is the intersection matrix of the curves in the base, which has this null direction, and the null direction is the uncontractable zero curve that corresponds to a little string. Then you can compute the flavor symmetry contribution to CL. So this contributes essentially Ka times the dimension of all the gauge algebras divided by Ka plus the dual Coxeter number associated with the gauge algebra. And this now has to be, can at most be equal to CL because this contributes to the left moving central charge. And if we now insert essentially the Dirac pairing eta ij, which is, as I said, the intersection numbers, you can derive this inequality that the level Ki times the dimension of the flavor group Fa divided by Ka plus the dual Coxeter number is less than or equal to 9 kappa p plus 2. Now you can use something that's called a strange formula by Freudenthal and de Vries, and what this tells you is essentially that the dimension of over 1 plus the dual Coxeter number is bounding the rank from above. Essentially, you can just check this by inspection for ADE. So if I take this and put this in here, I find that the rank of the flavor algebra has to be less than or equal to 9 kappa p plus 2. And if you recall, kappa p was equal to 2 for the heterotic LSTs. So then I get 20, the rank of the flavor group is less than 20. That's obvious already from the fact that this essentially is given by a K3, which can have pk rank, or which can have pk rank 20. Kappa p is equal to 0 for the type 2 LSTs, and in this case, we find that the rank of the flavor group is bounded to 2. Okay, so the flavor sector is much less interesting in this case because it's essentially trivial in all examples, and there's only very little room. It has to be less than or equal to 2 from this anomaly argument. But they have much more interesting one-form symmetries and defect groups, which relate the two algebras of the fiber and the base that define the theory. And if you remember sort of this double vibration structure in the beginning, under T-duality, these get exchanged. And we also discussed this in the paper. Good. So with this, I already want to conclude. I discussed 3 different projects. In the first one, we looked at the heterotic LSTs and their T-dualities. And sort of there's also a way in which sort of the singularity in the fiber and the singularity in the base is exchanged. We argued that the flavor rank is preserved under T-duality, even though kappa f is not. We discussed sort of different levels of complications, ways to get non-simply laced theories, ways to get twisted Lie algebras, and sort of ran this program and saw that this picture that I had in the beginning of moving T-duality across sort of going into circle compactification plus Coulomb branch, this takes you out of any of these classes, so you can have twisted Lie algebras being T-dual to non-twisted algebras and so on, which is, from the geometric point of view, is rather clear because this is just a property of the elliptic vibration that you chose. For the frozen singularities, I discussed that by fusing LSTs to supergravities, we could argue that the number of neutral hypermultiplets is unchanged, and we derived the frozen spectrum from the type 1 perspective for all ADE singularities, essentially using some representation theory for finite groups. And for the type 2 LSTs, I showed you a bound on the flavor rank, which came out to be either 20 or 2 for type 2 and for heterotic. And we got this from essentially worldsheet anomaly analysis. And I showed you fiber-based duality is, again, sort of induced by T-duality. So before I conclude, I want to give a little bit of commercial. There's a math and ML program in Harvard this fall. So we start with an opening and a closing workshop in first week of September and last week of October. And in between, we have different topics relating to number theory, knot theory, graph theory, interactive theory improving, and PDE. So if you're interested, this is the website. And let me know if be in contact if you want to know more about this. And with this, I conclude. Thank you.